So for now, let me introduce our speaker. It's Leonardo Maltoni from Sorbonne University, and he is going to talk about introduction to the quantized enveloping algebra.
Thank you very much. And can everybody hear me? Can you hear me?
You.
Okay, thank you. So before I start, I want to thank the organizer for giving me the opportunity to speak. And as Vanya was saying, I will cover the first two lectures of this introduction to quantum groups. And I will talk about the quantized enveloping algebra. So the first lecture will be about the description of the algebra. And in the second one, we will say something about its representations. So let me show you some references. So the principal reference, as Vanya was saying, is the book by Janssen, Lectures on Quantum Groups. But there is another important reference, which is the book by Lustig, Introduction to Quantum Groups. And for this talk, in this talk, we will also speak about Hopf algebra. We will give the definition in general. So there is another reference that I like, which is the book by Ettinghoff, Gelecki, Nikschik, and Ostrich, called Tensor Categories. So we can start. Okay, so we will have to introduce some notation. So in this first part, I repeat, I will just describe the quantized enveloping algebra. So as the name suggests, this is some kind of quantum deformation of the classical universal enveloping algebra. And so we have to start by some compatible data. So we start with G, a complex semi-simple Lie algebra. And as usual, we fix inside a Cartan subalgebra. And this gives us a root system inside which we fix a set of simple roots. And we will call W the Weil group. So we also want to fix a bilinear form, actually a scalar product, in the vector space given by extending the scalar of the root lattice to Q. And how is this defined? So we can give it on each irreducible component of phi. So by the formula alpha alpha equals 2 for any short root alpha. So we know that in each irreducible component, we can fix up to a scalar only. Also, I didn't say the most important thing. So W invariant scalar product. So we know that in each irreducible component, we can fix up to a scalar only one W invariant scalar product. So these conditions define our scalar product on the irreducible component. And we can deduce by that alpha alpha in general belongs to the set 2, 4, 6 for any alpha in phi. Okay, So we have, in general, so given a W invariant scalar product, we can show that we have this relation, the pairing lambda alpha check equals 2 lambda alpha over alpha alpha for any alpha in phi and any lambda in this space. And we know, so let us call lambda, capital lambda, the set of lambda inside here with this pairing integer for any alpha in phi. So what do we deduce if we compute the scalar product between lambda and alpha for any lambda in capital lambda and alpha a root? This, by this formula, is given by lambda alpha check times alpha alpha over 2. So by definition, this is an integer number, and this is either 1 or 2 or 3. So we get that this thing is an integer. Okay, so we will also call pi alpha for all alpha in set of simple roots, the fundamental weights. Okay, so let me move on. So I have to introduce some other notation. In particular, I will talk about Gaussian binomial coefficient. I didn't say it, but please interrupt me if you have any questions or if you cannot read what I write, because I have a tablet which is not, I'm not so used to it. So for any a integer, we'll define bracket a to be v to the power a minus v to the power minus a over v minus v inverse. And this is easily shown to be an element of this ring, the ring of Laurent polynomials in one variable. Actually, this is v to the a minus 1 plus v to the a minus 3 plus, and so on, v to the 1 minus a. So for example, bracket 1 is just 1, bracket 2 is v plus v inverse. Okay, so fix now n a natural number. We define the Gaussian binomial coefficient to be this fraction. So in the numerator, we have bracket a minus 1, down to bracket a minus n plus 1, divided by this product 1, bracket 2 to bracket n. So this is not so obvious, but one can easily show that this is, again, inside this ring.
Right, and this is left as an exercise to enthusiastic audience members.
Yes. Okay, so we will want to specialize these quantum numbers and quantum binomial coefficients to elements of a field. So let K be a field, and Q, for the moment, just be a unit of this field. So we have a natural morphism of ring going from this ring of Laurent polynomials with integer coefficients to K, sending V to Q, because we have chosen Q to be a unit. So we fix A with V equal Q to be just the image by phi, of our bracket A. And in the same way, this will be the image of the quantum binomial coefficient. Okay, so we have already fixed the R field. We want to impose some other assumptions before we get started with the definition, the actual definition of U. So we set Q alpha for any alpha in pi to be Q to the alpha over 2. So this is either Q or Q squared or Q to the third. Okay, so we want to suppose that Q alpha squared is different from 1 for any alpha in pi. And this is the last piece of notation, I promise. We have bracket A alpha. This is defined to be bracket A specialized with when V is Q alpha, and in the same way with quantum binomial coefficient. Okay, so if there is no question about the notation, I can proceed with the definition of our quantized enveloping algebra. Okay, so we want to define U. We will denote U, the quantized enveloping algebra over of G, to be the K algebra, so associative K algebra, with a unity generated by these elements. So we have E alpha, F alpha, K alpha, and K alpha inverse for all alpha simple root, with the following relations. So the first relation describes how the K alpha interact with themselves. So what we will call the Cartan part. So we have an obvious relation that says that this is not just a notation. So K alpha and K alpha inverse are actually inverse of each other. And we also impose that K alpha K beta equals K beta K alpha for any alpha beta in pi. So what we get is a commutative subalgebra generated by the K alphas. And after the definition, I will make some remark about this subalgebra. Okay, so the second relation tells us how the E alphas interact with the K alphas. So it is a conjugation. So K alpha E beta K alpha inverse. This has to be Q to the alpha beta times E beta. So recall that for alpha a weight in general, but in particular, if alpha is a root, alpha beta is an integer, so this is well defined. And we have this relation. And relation 3 is the analogous one for the F's, so the negative part. So K alpha F beta K alpha minus 1 equals Q to the minus alpha beta, this time, F beta. The fourth relation tells us how the E's and the F's interacts with each other. So it tells us that E alpha F beta minus F beta E alpha, so the commutator between the two, equals delta alpha beta, so 0 if the two roots are different. And otherwise, it is this fraction, K alpha minus K alpha inverse, Q alpha minus Q alpha inverse. And here you can see why we supposed that Q alpha is different, Q alpha squared is different from 1, because otherwise this denominator vanishes. Okay, so for up to now we have some relations defining interaction between the different generators. We want other two relations that specify how the E's interact among themselves and the F's too. So the fifth relation, for the fifth relation, we will fix two different roots, alpha and beta, and we inside pi, and we will call R to be this number, 1 minus beta alpha check. So if you have seen the presentation by generators and relation of semi-simple Lie algebras by Serre, then these relations should recall you in some sense those one. But we will see in particular how they are related. So let us call R this thing. Then our relation is that the sum for I from 0 to R of minus 1 to the I, quantum binomial coefficient R over I specialized when V is Q alpha, times E alpha to the I, E beta, E alpha to the R minus I. And we want this to be 0. So this is the worst formula from this definition. So let us do some examples. So for example, when we have B alpha check equals 0, so remember that B alpha check, beta alpha check, when alpha is different from beta, is a non-positive integer. So this number is at least 1. So this sum is always non-empty. And in the case beta alpha check is 0, then R is 1, and we just get that E alpha and E beta commute. Another example is when beta alpha check equals minus 1. So the sum has 3 terms, and we get E alpha squared, E beta, minus, I will write for the moment like this, E alpha, E beta, E alpha, plus E alpha, E beta, E alpha squared equals 0. So this is just the quantum number 2 specialized when V is Q alpha. And this is just, as we saw, Q alpha plus Q alpha inverse. So in these two cases, this is what fifth relation look like. Look like. And the sixth relation is just the same thing, but with the F's. So again, let's say alpha beta R as before, and we want this formula to be satisfied by the F's. So these last two relations recalls, as I said, the Serre relations of commutation between element in the semi-simple Lie algebra represented by generators and relations. So are there any questions so far?
maybe we should make a little comment. So
yes,
what's kind of a connection with the classical presentation of the semi-simple Lie algebra? Well, E alphas and F alphas are just root vectors, and K alpha should be thought as Q to power H alpha. Then, for all relations that we know about for semi-simple Lie algebras, there are easiest possible Q deformations that we can write. Yeah, this is precisely what happens.
I don't know, can one say more about the origin and motivation for the formulas? For example, why is it important to introduce Q to the power of HI and not work with HI itself?
so I'm not that familiar with that motivation, I admit, so maybe Vanya can answer or someone.
Well, I could try. Let me give you a simple-minded answer for now. If we use H's, then this formula will become more ugly.
Okay.
And then, of course, there is a theory of, as Roma knows, the theory of this quantizations in this sense. So we quantize a certain bialgebra in a certain way. We quantize certain Poisson what's the name? Poisson bialgebra in a certain way.
Formulas will be more ugly and they will be not polynomial in Q all around.
In H bar, well, yes.
Yeah. So H bar is log Q.
That's right. And an interesting feature is that, you know, whenever you want Q deformation of a semi-simple Lie algebra to appear in nature, this is the Q deformation that appears. Although there is no, I don't know any conceptual reason for that.
No, there is a conceptual reason is that this is the only deformation at the level of tensor categories.
Okay.
So there is a theorem that if you have a simple Lie algebra, then the only deformation of a tensor category and also the only deformation of braided tensor category is given by this.
When you say the only, it means some up to
isomorphism, yes.
Isomorphic up to completion, or what is the?
Well, this is a theorem about formal deformations. So, so it's deformations are unobstructed, and the space of deformations is one-dimensional.
Right, but this is more than that, because there is this nice form over Laurent.
That's also true. Yes, there is a nice form. That's right.
But Pasha, we can choose various Poisson structures.
That's right, but they will all produce the same. I mean, so this is the only non-trivial deformation of the tensor category. So other Poisson structures will, it's possible to have different Hopf algebra structures, which will give you the same tensor category.
Oh, okay. So this is not quite an explanation of why exactly we need to do these formulas.
Okay, there is, if you require, for example, that your deformation is equivariant with respect to the torus, then it will be more or less the only thing you can do. There is something that is called Reshetikhin twists, but they're kind of rather trivial, and basically that's the only thing you can have.
Okay.
Thank you.
And yes, you don't need to be a seminar organizer to ask questions. That's just a remark to the audience. Maybe Leonardo can continue.
May I confirm if this is a unique extension to, in terms of tensor categories, or it's unique if you want quasi-triangular structures?
Actually, it's unique even if we just consider tensor categories, but there is a subtlety. There is a modular space of deformation of tensor categories and modular space of deformations of braided categories. and they are both one-dimensional and smooth, but one is a double cover of the other. The parameter of deformation of tensor category is q minus 1 squared, or log q squared. And parameter of deformation of braided categories is just q minus 1, or log q. So one is, differs from the other by the map z goes to z squared, which is a branch double cover.
Thank you.
Can I ask a question which is trying to make a more precise Roman question? So when you look for something that's not just at the point, not just at the completion of a parameter, but more integral, I mean, you end up having a quantization not of the enveloping algebra, but there is this extension, central extension to ki, not ksquare, etc. There is this extra relation. So is that related to what you were saying about the deformation space, or is that something else?
I didn't quite understand. Can you?
So what I mean is that this is not a deformation of the enveloping algebra, okay? There is this extra, there's a kernel when you do q equals 1.
Yes.
So can you explain that? Or I mean, why do we have to do that?
Yeah, so what will happen is when we discuss representation theory, it will turn out that every representation of Lie algebra will have not one, but 2 to the rank analogs, where k's will have eigenvalues either plus powers of q or minus powers of q. And so these representations, somehow you cannot get rid of them. You cannot write down an algebra which will not have those representations. So this is a somehow fact of life. I don't know. Maybe I have to think about what is the conceptual explanation for that.
If you were to take to specialize the parameter to a generic value, you would not have to do that, correct?
Yeah. Well, I mean,
so that has to do. You would feel like there is a 2 to the n, maybe cover of there's a modular space somewhere. There's a cover, and maybe you can split in at a certain point, but globally something is not split.
That's right. That's right. Yeah, something like that.
Thanks.
So thank you. And if there are no more questions, I will pass to the first remarks about this definition. So as I said, I want to make some comments about these subalgebra generated by the k alphas. So the first remark is that if we call U0 to be this subalgebra, so generated by all k alphas and k alpha inverse with alpha simple root, then this is commutative. And actually, it is a Laurent polynomial ring in several variables. We can define, we can use this notation. So for gamma in the root lattice, we set k gamma to be the product of all k alpha to the power m alpha, where our gamma is written as the sum of m alpha alphas for alpha in pi. So this makes sense because we can take a power of k alpha with m alpha an integer. And we obviously have that k gamma times k delta equals k gamma plus delta. Okay, so the second remark is that with this notation, we can generalize relations 2 and 3. So recall they were about conjugation of E alphas and F alphas by elements in the Cartan part. So we can generalize 2 and 3 with K gamma E alpha K minus gamma, which is the same thing as K gamma inverse, equals Q to the gamma alpha E alpha. And in the same way, K gamma F alpha K minus gamma equals Q to the minus gamma alpha F alpha. Okay, so these two remarks allow us to extend the definition in the following way. So we could define the quantized enveloping algebra extending the Cartan part. So we could extend the Cartan part by choosing a subgroup, containing the root lattice inside, so we call it capital gamma, inside this abelian group, such that for any gamma in capital gamma and alpha in phi, we have gamma alpha is an integer. So we know that this is true for the root lattice, but we can extend, and for example, we have seen that this is true for gamma equal lambda. So for example, we can take lambda. And then we can replace the generators K alpha and K alpha inverse by K gammas with gamma in capital gamma, and relations 1, 2, and 3 so from 1 to 3 with remarks 1 and 2. So these two things. And this allows to extend the Cartan part. So let us move on. Now, one of the most important things that we will discuss in this lecture is the Hopf algebra structure on this quantized enveloping algebra. So before we describe the structure of U, let us recall what a Hopf algebra structure is. So let A be a K algebra with unit, and delta from A to A tensor itself, S from A to the opposite algebra, and epsilon from A to K be morphisms of K algebra, of K algebras. We say that A delta epsilon S is a Hopf algebra if the following axioms are satisfied. So before I state the axiom, let me give a name to these morphisms. So this is called the co-multiplication or co-product. This is the antipode. Maybe I should have written epsilon before. And epsilon is the co-unit. So our axioms are the following. The first is called co-associativity. And you can understand why. So it's the commutativity of the following diagram. If we take A and we apply delta, we land in A tensor A. Then we can apply delta on the first factor and the identity on the second and get A tensor A tensor and get in A tensor A. Or we can do the same thing at the beginning, but then applying delta to the second factor and getting here. And we know that here we have a canonical isomorphism, and we want this diagram to commute. So in formulas, this is just 1 tensor delta, delta equals delta tensor 1 delta. And as I said, you can see why it is called co-associativity, because this is just associativity with arrows reversed and with a co-multiplication instead of a multiplication. The second axiom is the co-unit axiom. And it says that if we take A and we do delta, sorry. And then we apply the unit, the co-unit on the first factor, for example. Then we get to K tensor alpha, tensor A, and we know that these are isomorphic canonically, and we want this to commute. And in the same way, we want the other diagram that we can obtain in the same way by applying the co-unit to the second factor. So we want also this to commute. And again, this is just like the unit axiom, but with arrows reversed. And finally, we want the antipode axiom. Which is the commutativity of the following two diagrams. So we can apply co-multiplication, then antipode on the first factor, and then multiplication, by the way, I will denote by M, and we land in A. And we want this to be the same thing as this arrow, which is the unit after the co-unit. So where the unit, iota, is the arrow going from K to A, sending an element X of the field in X time the unit. And we want this to commute, and also the other one. Okay, so before passing to our case, let me do some examples of Hopf algebras. So if we take, for example, G, a finite group, then the group algebra is a Hopf algebra. And maybe as an exercise, you can try to show that delta G equals G tensor G for all elements, for all G in G, then extended linearly. and S of G equals G inverse for any element of G, and then extend it linearly, and epsilon G equals 1 is define a Hopf algebra structure. And if G is a Lie algebra, then the enveloping algebra, the classical one, is a Hopf algebra. This time we will impose delta of x equal x tensor 1 plus 1 tensor x, s of x equals minus x, and epsilon x equals 0.
And this is for x and g.
Yes, yes, this is for x and g. And then we extend to the whole enveloping algebra. And finally, there is another example, which is, if we take G to be a linear algebraic group, then the coordinate ring is a Hopf algebra. And here you can just take the axioms defining a group, which we know, in which we know the arrows are morphism of algebraic variety, and then applying the equivalence with K algebras and get all the diagrams defining the Hopf algebra structure. Okay, so let me pass. Yes?
Maybe an exercise is that epsilon and s are uniquely determined by delta if they exist.
Okay, so so you said epsilon, so sorry, S is determined by epsilon and delta if they exist?
No, so we know that if you know, so when we define a group, we define a product, and then existence of unit and inverse are properties.
Okay, yes. Okay.
Yes, and another exercise to show that the antipode is an anti-homomorphism. That also follows from the axioms.
Yes.
Sorry, and are these the only sort of interesting Hopf algebra structures on these algebras, or?
No. No. For example, no, there are many other structures. Like if you take enveloping algebra, for example, and take formal power series in H bar with values in enveloping algebra, then this is isomorphic to the formal version of the quantum group. So quantum group, actually, if you take the formal version, it is isomorphic to the ordinary enveloping algebra, simply because ordinary enveloping algebra doesn't have non-trivial deformations.
As an associative algebra.
Right.
Okay, thank you.
Okay, so now we want to finally give our quantized enveloping algebra the structure of a Hopf algebra. So we want to define on U a Hopf algebra structure. And we will use the following morphisms. So there's a lemma stating that there exist unique morphisms of K algebras, delta from U to U tensor U, such that on generators it is defined the following way, such that delta E alpha is given by E alpha tensor 1 plus K alpha tensor E alpha. And then for F alpha, we have 1 tensor F alpha plus F alpha tensor K alpha inverse. And for K and K inverse, we just have K alpha tensor K alpha and K alpha inverse tensor K alpha inverse. For S, we want zoomorphism and anti-automorphism such that E alpha is sent to minus K alpha inverse E alpha. F alpha is sent to minus F alpha K alpha. And K alpha is just sent to its inverse. And of course, K alpha inverse is sent to K alpha. And finally, the easiest one is the co-unit from U to K, which is just on, on K alpha, this is 1, and on E alpha and F alpha, we get 0. So every definition here is for alpha in pi. So to prove this lemma, so to prove that this definition actually define in a proper way morphisms of K algebras, we have to do many computations. So maybe I will do some of them, but before, let me say what are the consequences of this lemma. So one first remark is that we can state a property of the square of S. So S is an anti-automorphism, so its square is an automorphism of U, but it is not the identity. So one can check that S square of U equals K to the K2 row inverse U K2 row, where as usual, rho is just half the sum of positive roots, which is the same thing as the sum of fundamental weights. So one can check that this, maybe as an exercise, you can check that by the definition of S, one deduce this. But the proposition that we wanted from the beginning is the following. So U with delta epsilon S is a Hopf algebra. And this is easy once we have the lemma, because you can just verify all these, the commutativity of all these diagrams on generators. And this is rather easy. It's just some computation, but nothing particularly difficult. So before we have a little break, let's just give a sketch or some ideas in the proof of the lemma. So I won't give all the details because there are too many, but so we have to, to check all these definitions, we have to check that relations are preserved. So we have to check that the images of the generators respect some relations. So for example, relation 1 is really easy because K alpha is always sent to, like for example, K alpha tensor K alpha, or K alpha inverse tensor K alpha inverse, or the inverse of K alpha, etc. So the commutativity and the inverse property are just immediate. So this is easy. Let us do, for example, relation 2 and 3, because there is a way for doing them at once and introducing an important feature of our algebra. So U is Z phi graded. and we can introduce this grading by setting the degree of K alpha and K alpha inverse to be 0, the degree of E alpha to be alpha, and the degree of F alpha to be minus alpha. And then we can check that all relations are homogeneous with respect to these grading. So the grading that we defined on the free algebra actually descend on the quotient, so on U. So this define a proper grading on U. So why is this useful now? Because we can deduce from relation 2 and 3 that if U belong to the graded piece, to the gamma graded piece of U, then K, let's say lambda, U K lambda inverse is just Q to the lambda gamma U. So this is again a generalization of relation 2 and 3. And we can just remark that our definitions of the images of the generators all preserve the grading. So if we put an induced grading on the tensor product of U with itself, then all these relations are homogeneous, and then it is easy to check relation 2 and 3. So let me do an example for relation 4. For example, we can check that S preserve this relation. So remember that we want, so for S, remember that we want S to be an anti-automorphism. So in particular, we want to check that the commutator of S E alpha with S F beta, we want this to be minus delta alpha beta S K alpha minus S K alpha inverse over Q alpha minus Q alpha inverse. The minus is because...
So as I mentioned, it actually you don't have to check it, because if S satisfies antipode axiom, it automatically is an anti-homomorphism. This follows from the axioms.
But you don't have anything to check, because S is not defined yet, right?
Ah, okay, yeah.
So yes, well, yes, this is the proof of the lemma. So we have to check that S is actually a morphism.
Oh, you're okay. So you're proving that it's well defined.
Yes, that's the thing. Yes, so to prove that, we have to check that this, so this is, we want to see this, and let us compute this commutator. So we have the commutator of minus K alpha minus 1 E alpha minus F beta K, K beta. And we want this to be equal to that. So this is K alpha minus 1 E alpha F beta K beta minus F beta K beta K alpha minus 1 A E alpha. So here we just use relation 2 and 3 to switch F alpha with K beta. So so we do something else, sorry. Before we exchange K alpha minus 1 with K beta, because they commute. And then we, so this is K alpha minus 1 E alpha F beta K beta minus F beta K alpha minus 1 K beta E alpha. And then we switch these two and these two by relation 3 and 2 respectively. And we get So the first term is unchanged. In the second term, we get k alpha minus 1, f beta, e alpha, k beta, but we have to add some power of q, because when we switch f beta with k alpha minus 1, we get q to the alpha beta by relation 3. And when we switch k beta with a alpha, we get q to the minus alpha beta. So actually they get simplified, and we got k alpha inverse times the commutator of e alpha f beta times k beta. And now we just apply definition, so the relation 4, and we get k alpha minus 1 times delta alpha beta, k alpha minus k alpha inverse over q alpha minus q alpha inverse times k beta. And so this is easy to check that this is just delta alpha beta times k alpha minus 1 over k alpha minus q alpha minus q alpha minus 1. Is because when alpha is different from beta, then all this is 0. And when they are equal, everything commute, and k alpha minus 1 gets simplified with k beta, which is equal alpha. And this fraction is the same thing as this one, by the definition of S on k alpha. Okay, so for relation 5, I will just say that this is a long computation, and then if you want to do it as an exercise, then do before the case, do first the A2 case. And I'm sure you will not want to do the other cases. But okay, so let's have a break here.
Something tells me that we don't want to do this case publicly as well.
Yeah, we won't do this case. You can find it on the notes.
I mean, there is a kind of concise way of doing these calculations, but it's not important right now. I mean, there is a way to do it so that it won't be unpleasant.
Okay, so I know just the way by Janssen, and that is very a little.
And not to mention that different people find different things to be pleasant and unpleasant. That's a little bit subjective.
And there are also people who enjoy things which are unpleasant.
Okay, all right. So maybe it's a good time to make a break.
Yes.
So Leonardo, how long a break do you want? So let's say 10 minutes?
Yes, okay, 10 minutes.
Okay, guys, we do a 10 minutes break.
I just want to mention that there's a question in the chat that maybe Pavel,
I'm sorry.
I think maybe Pavel can address it. I don't know, now or at some point. It's,
Pasha.
Again, a variation of my question. A different take on it. But yeah, I don't know if we can, something that would be nice to address at least at some point.
Well, I mean, from what I understand, and I'm not sure if, okay, how about this? Let me pause the recording, and people can ask questions that they want to be asked off record. And I suggest we don't have fun doing the exercise and declare the proof of the lemma finished.
Yes, so this was already the plan. So, and okay, so we can now start to see one first application of this Hopf algebra structure. So the real applications will be, we will see them in the next lecture when talking about representations. But now we can already define a representation of our Hopf algebra U over itself. So in general, when you have a Hopf algebra, so the same datum as before, we can give to A the structure of an A module in the following way. So first, we give A the structure of an A tensor A module by letting A1 tensor A2 act on B, where these three are elements inside A, by left multiplication by A1 and right multiplication by S of A2. So here we are using the antipode to get this right action into a left one, actually. So, and secondly, we use delta to pass from this A tensor A module structure to an A module structure. So we get an A module structure via delta. So if A, and so we denote, which we call the adjoint representation. And denoted by add. So if A is an A, sorry, and the coproduct of A is given by this sum of tensors inside A tensor A, then what we mean by using delta for getting from this to an A module, we mean that add A of some element B, it is just the sum of AI times B times S of AI prime or OI. So this is the general construction for the adjoint representation of a Hopf algebra. And you can check on the examples that we made that, for example, for the group algebra of a finite group, you get that the adjoint representation of G computed on an element, let's say X, it's G, X, G inverse. And for the enveloping algebra of a Lie algebra, you get that the adjoint representation over X of an element U, it's X bracket U, bracket XU. Okay. So let us pass to our example. So our case. So let us apply this to U. So what do we get? If we perform the preceding construction, then we get that the adjoint representation is given on generators by these formulas. So if we apply the adjoint representation on E alpha, we get this operator sending U to, so recall that delta E alpha is E alpha tensor 1 plus K alpha tensor E alpha. So we get E alpha U by this, and then plus K alpha U, and then the antipode computed on E alpha, which is minus K alpha minus 1 E alpha. So this is just E alpha U minus the conjugate by K alpha of U times E alpha. In the same way, if we apply this to F alpha, we get, so recall that F alpha is 1 tensor F alpha plus F alpha tensor K alpha inverse. So we get U times minus F alpha K alpha plus F alpha U K alpha. So this is F alpha U minus U F alpha K alpha. And the easiest one, so applied on K alpha, here we just get K alpha U K alpha inverse. Okay, so before we proceed, let us observe that we can use this adjoint representation to restate our relations 5 and 6, so the Serre's relations, in a much more compact way. So relations 5 and 6 can be rephrased as, so the relation 5 become that the adjoint representation of E alpha to the R applied to E beta equals 0. And relation 6, that if you apply the adjoint representation F alpha to the R to F beta K beta, then we get 0. So we can check as an exercise that these are actually equivalent to our previous formulation of relations 5 and 6.
And maybe it's worth pointing out that since odd is an algebra homomorphism, we can rewrite number 5 as adjoint of E alpha to power R applied to E beta equals 0, which is precisely the Serre relation.
Yes.
For semi-simple algebra.
So let us.
Maybe it's not worth pointing out. It's kind of easy.
Yes. Okay. Okay.
Actually, this is the way to check the fact that coproduct is well defined on Serre relations. You can use this to make this computation easier.
Yes. Okay.
And prove this lemma that is unpleasant.
Okay,
or pleasant, depending on your perspective.
So let us go on if there are no questions. And let us come to the last part of the description of the quantized enveloping algebra of this lecture, which is the triangular decomposition. So this is again a feature which reminds us some feature of the classical enveloping algebra, but in that case, this is just given by an application of Poincaré-Birkhoff-Witt theorem. So here we will have to find some analogous statement. So we already defined U0 to be the algebra generated by the K alpha and K alpha inverse. And we also define U plus to be the algebra generated by E alpha, the E alphas, and U minus to be the opposite part, so the negative part, generated by the F alphas. Okay, so the theorem is that if we take the multiplication morphism from this triple tensor product to U, this is an isomorphism of vector spaces. And in particular, if we choose a basis of these three subalgebras, so if Yj is a basis of U minus and K mu is a basis of U0 and Xi is a basis of U plus. So I denoted the basis of U0 by K mu because actually we know that U0 is the Laurent polynomial ring in these different variables, so in the variables K alpha, so we get a basis by all monomials. So if we have these three bases, then Yj, K mu, Xi, so this set form a basis of U. So before recalling the ideas of the proof, let me also make a remark, and that will allow us to introduce an important automorphism of U. So we can define an automorphism, of U, automorphism omega of U by omega E alpha equals F alpha and omega F alpha equals E alpha and omega K alpha equals K alpha inverse, and obviously omega K alpha inverse equals K alpha. So this is easy to check. You can just check that the relations are satisfied and you get this automorphism, which has obviously that omega square equals 1. And the theorem, so we can get a corollary of the theorem by applying this automorphism, which is the opposite triangular decomposition. So U plus tensor U0 tensor U minus is isomorphic to U by multiplication. Okay, so let us give some idea of the proof. Okay, so we will proceed by 2 steps. So I won't give all details again, but the first step is to do first the case of a larger algebra. So we will consider U tilde to be the algebra with same generators as U, but with only relations from 1 to 4. So we exclude Serre's relations. So K algebra okay, so why we do this? Because so relations 5 and 6 get thing more complicated, and it is easier to describe a basis of this algebra, and then we can pass to U. So there is maybe a question in the chat. So the question is why we know that U0 has K mu as a basis. So we know that, maybe I can go back to first remarks. So we know that the algebra generated by K alpha and K alpha minus 1 is commutative, and it is just, we can define, so it is just a polynomial algebra in the variables, a Laurent polynomial algebra in the variables K alpha.
No, I think the person who asked this question is right, that it's not clear that K mu are linearly independent. In fact, it is not clear that your algebra is not very small. I mean, it could be just one dimensional or something like that, a priori. If you put some relations, you may get an algebra which is very trivial. So this theorem, the point of this theorem is to show that the algebra is right. So, okay, so there is a remark that so the independence of K mu is something that you have to prove also.
Yes.
And that's part of the, I mean, this is all proved by this proof that you're describing. What is clear is K mu are a spanning set.
Yes. Okay. So yeah, maybe I was just, sorry. So you're right. So maybe this is not so clear. So maybe I will just call this basis let us say H.
Well, we can say that basis of K mu's where mu are in some subset. How was this?
No, but I think part of the statement is that U0 is the Laurent polynomial algebra in K, in the case. So that K mu is a basis of U0. This is part of the theorem. It's not obvious, but it's a part of the theorem.
Yes, perhaps this should be written down.
So let me. Okay, so thank you for the remark. And what we, so okay, so let me restate what I was.
I have a suggestion. So how about in the statement of the theorem, maybe to the right, let's scroll up. Well, to the right of this in particular, you add a statement that K mu's form a basis of U0.
Okay, so and K mu with mu in Z phi is a basis of U0.
Yeah, thank you.
Thank you. So, so what I wanted to say, so now maybe it will be clearer, is that if we take this U tilde, then to be the K algebra generated by the same regenerators, but with only relation 1 to 4, then we can define U tilde minus, U tilde 0, and U tilde plus to be the analog of U tilde, U minus, U0, and U plus inside U. So generated, the negative part is generated by the F's, the Cartan part by the K's, and the positive part by the E's. Then we have the analogous statement saying that this map is an isomorphism. And how do we prove this? We prove this by seeing exactly that that the monomials given by f a alpha 1, f a alpha 2, f a alpha k, k mu, e beta 1, e beta h form a basis where we take alpha I, beta j, and mu in the root lattice. So what I mean here is that we can take any sequence of simple roots. So sorry, not in the root lattice, but in the set of simple roots. So let me say better. Alpha I and beta j are are simple roots, and mu is in the root lattice. So this contains in particular that the k mu's are linearly independent.
In this large algebra.
Yes, in U tilde. Yes, I was from a basis of U tilde.
And also it says that U tilde plus and U tilde minus are free algebras on generators is and x.
Sorry, can you repeat?
So U tilde minus and U tilde plus are free.
Yes, exactly. Because yes, any sequences, any different sequence of simple root gives a linearly independent element. So okay. So I don't know if I have time to give all the details of the proof of this, but maybe we can just give a sketch. So the idea is that
so maybe before we go to a sketch, it's worth pointing out that the same statement appears when you study semi-simple D-algebras and like Kac-Moody algebras. And the proof in the quantum case is very similar to what we have in the classical case.
Yes. So maybe I will just, then I will just describe the idea. So it's
so maybe I can make a quick comment that so Poincaré-Bergov-Witt theorems. So there are actually two kinds of proofs of them, or maybe more than two, but the purely algebraic proofs are like the two kinds. So one is based on so-called diamond lemma. So basically on playing around with relations and bases and the combinatorics. And another is by constructing representations. So if you, so the hard part of PBW theorem is to show that some monomials are linearly independent, and to show that they're independent, you can construct an action of your algebra on some vector space. And if you show that they go to independent linear operators, then they're independent in the algebra. And this latter method is what's used in this case.
Yes, exactly. Thank you. So in fact, what I was going to say is exactly that one can define representations of U tilde over a vector space so let us call it K prime VI, where I is a sequence of simple roots, and K prime is any extension of K. So this is, and okay, so one can define a representation of U tilde over this vector space, and maybe I can give formulas. So by f alpha applied to vi equals v alpha I, so the sequence that we get by putting alpha in front, then k alpha times vi equals c alpha q to the minus alpha the weight. So I will specify the notation afterwards, where c alpha is a unit in the field. So we have to choose a set of elements in the field different from 0 for any alpha in pi. And this defines this representation. And we denote by the weight of a sequence just the sum of the roots appearing in the sequence. And finally, E alpha applied to Vi, this is equal to the sum for all j between 1 and k, where I use this notation, for which beta j equals, alpha j equals alpha of this fraction. Sorry, but I didn't remember the formula, but
so we essentially commute E alphas past F alphas and
yes.
use the cross commutation relation.
Okay, so one should check that these three formulas define a representation, but the comment of Vanya is just that. So once we have the first two, then the third is what it should be. Then we have this representation, and then we can apply. We can suppose that a linear combination of our monomials is 0, and apply it to, then we can consider the representation. So we call this representation mk prime C underlined, where C underlined is the set of our coefficients different from 0. So there is a representation of this kind for any choice of extension K prime and sequence of coefficients. So we can consider the representation M K prime C prime tensor M K prime C, where C prime is just 1 for all alpha. So this is not a C prime alpha is 1 and C is arbitrary. And then we apply, so suppose a linear combination of our monomials is 0. We can choose I0 yeah, but let us suppose that not all the AI mu j are 0, so we can choose an I0 such that there exists mu and j with a I0 mu j different from 0 with the weight of I0 maximal with this property. And then we apply our vector, our combination. Oh, sorry. To the vector V empty set, tensor V empty set inside this representation.
Something is wrong. I think one of these m's should be twisted by the automorphism omega.
Oh, yes, you're right. So
Yes.
actually we can, yes, is the second one. So I didn't define, yes, thank you. So I will just use this notation where this notation means that we twist the representation by omega, so the action of the E alpha get twisted with the one of F alpha, and K alpha is got to its inverse. But I don't want to do all the computation. So when applying this to this vector, using that tensor product of representation, one can get that one can get a description of, so let me say, then one can use a description of delta Aj and delta Fi, which is given in the book by Janssen, which allows us to write them with some coefficients as a linear combination of some tensor product that allows us to write this sum as the following, to deduce from this vanishing, because we know that this element has to be 0, the following sum, sorry. So one can use given to deduce that the sum over all mu's of a I0 mu j q to the power mu weight j c mu equals 0, where c mu is a notation for the product C alpha to the M alpha, if mu is the sum M alpha alpha. And by this formula, then we can conclude that as this has to hold for any choice of non-zero element C alphas in any extension of K, then all these coefficients have to be 0. But then we have our coefficients AI0 mu j, and we know that some of them has to be non-zero, and the power of Q, which is a contradiction. So maybe this was not so clear because I keep some passages, but the idea
Maybe
is what
a comment. Could you please
Yes.
scroll down a little bit?
Yes.
So what's no up? Aha, yes. So this vector. So how does this work? So you know, we apply this this non-commutative polynomial to the vector where v empty turns v empty, and we sort of look for the highest term in natural order. So this term will have vi as the first factor, and then the sum of vj's with certain coefficients. And we just can see that the coefficient is this sum over mu, which is written in line second from below. This one, yes. And then you can see that in natural order, you can impose all other terms will be just zero, will be just less in that order. So that's how we conclude that the sum is equal to zero. Do people have questions?
Yeah, maybe I should make a comment that in fact, there is something that is called quantum double construction, which we hopefully will discuss. Yes, will we discuss it or no? I don't know when we talk about our metrics.
Perhaps not.
But in any case, there is that's really also answers the question how to guess all these formulas. In particular, how to guess the formula of commutator between E's and F's. And this construction allows you to basically, this theorem becomes obvious when you construct the quantum group by this construction. So this computation becomes unnecessary if you use that approach.
Okay, thank
All
you.
right, maybe we can get to the second part of the problem.
Yes, then this will conclude my talk. So for up to now, we have proven that in this larger algebra U tilde, we have the triangular decomposition that we wanted, and now we want to pass to step 2 about U. So we know that we have a natural morphism, a quotient morphism from U tilde to U, which is given by imposing relation 5 and 6. And so we will call the kernel of this morphism I. So we know that I is the two-sided ideal generated by all right-hand sides of relations 5 and 6. So all those sums with signs, binomial coefficients, and products of powers of E alpha and E beta.
Although I would guess those are left-hand sides.
Yes, thank you. If not, the right-hand side are 0. Sorry. Okay. And now we want also to introduce that other two ideals. So we introduce I plus inside the positive part to be the ideal generated by the left-hand sides of relation 5. So two-sided and inside U tilde plus. And I minus the analogous in U minus, so the ideal generated by left-hand sides in relation 6. So what we can prove, what one can prove is that one has that u tilde over u tilde plus over I plus is isomorphic to u. So this is not obvious, but one can prove it rather easily. Plus, sorry. And the same thing for u minus. So one can prove it that just the positive part can be presented as the part generated by the E alpha and only relation 5. And the same thing for the negative part. And the last thing that we need is that one can show that our I, our two-sided ideal, is just the image by the multiplication map of this ideal. So I minus tensor u tilde 0, tensor u tilde plus u tilde minus, tensor u tilde 0, tensor I plus. Then
and
we have
the proof. Oh, sorry. And the proof are just as in the classical case, essentially.
Yes. Yes, essentially, yes. And we have now all the ingredient because we know that this, by step 1, that this is an isomorphism. And by the last statement, last claim, we know that this pass to quotient if we quotient on the left-hand side by this ideal, and on the right-hand side by our ideal I. So we know that this equals u. And now using some general fact about quotient in tensored algebras, we can get that this is just u plus over I plus, tensor u tilde 0, tensor u tilde, sorry, this was a minus. U tilde plus over I plus, and the other ingredient that we use is that this is just u minus. Then we can observe that u tilde 0 is the same thing as u 0 because one can prove that relation 5 and 6 do not affect the Cartan part, and this is u plus. And if you follow these maps, we get our multiplication. And this concludes the proof and the first lecture, I think. So thank you very much for your attention.
Attention is easy, given talks is harder. So let's thank Leonardo for the talk. Are there any questions?
Yeah, maybe I want to make a comment that this is not yet a quantum analog of Poincaré-Berghoff theorem as we know it, because, for example, so the full PBW theorem, which will, I guess, be discussed later, is that also so the space U plus has a grading by the root lattice, and every homogeneous subspace is finite dimensional. And the full theorem says that the dimension of the subspace is the same as Fourier algebras. We haven't proved this yet, but it will be proved later, I suppose.
That's right. Okay, anybody who is not an organizer and who wants to ask a question or make a comment?
There was this involution defined What's the classical limit of that evolution? Omega, I think it was called.
Yes, you have, sorry. This one?
Yeah.
So there is, so you have an involution of any semi-simple Lie algebra given by, so you have the Cartan decomposition of the Lie algebra. You can define an involution in the same way, but you have, so for the Cartan part, I think you have to
well, it's just H alpha going to to minus H alpha.
Yes, to
That's
minus
right.
H alpha, yes, yes.
So this is what it's called Cartan involution.
Yes.
Wait, but this doesn't, isn't this not quite like the Cartan involution? Isn't there like a sign? Oh, I see.
So
you mean that it could send F alpha to minus E alpha or something like this?
Yeah.
Oh, no.
Well, I mean, all of these are related by some simple transformation. It doesn't really matter.
Sure.
More questions?
I was curious. Pavel, you said that you might have a Bergman-Diamond lemma approach to the proof of this triangular decomposition.
Actually, the Diamond lemma is normally used when you have quadratic algebras more often. So here you have higher order relations, so it's harder to use this kind of. But you could do it, I think. I mean, this is really an approach when you construct some kind of Grobner basis, and you could do it here as well. So basically, you have this algebra is a filtered algebra where the degrees of E alpha and F alpha are equal to 1. And then if you take associated graded, then the commutator of E alpha with F alpha will be not this expression with K alphas, but just 0. So that algebra also is a Hopf algebra. It's a nice object. And for it also we have this Poincaré-Berghoff theorem. So you have to show that this filtered deformation is flat. And for this kind of thing, you can use Diamond lemma. Yes.
More questions? Let me stop the recording.